Thank you. Yeah, it's wonderful to be back at IPAM. Thanks to the organizers for making it possible. I'll be talking about a field that we have been pursuing for maybe a decade or almost 2 decades now. It's known under the title exact factorization. Now you will see in a minute what this exactly means. It's about treating matter in an ab initio sense. So we have to start from the full Hamiltonian, the Coulomb Hamiltonian, of everything that is around us. So kinetic energy of the nuclei, kinetic energy of the electrons, nuclear-nuclear, Coulomb repulsion, electron-electron repulsion, and the electron-nuclear attraction. So capital R double underline, that's the collection of all nuclear coordinates. Likewise, little r double underline is all the electronic position vectors. And with this Hamiltonian and possibly a time-dependent external field, laser, let's say, simplest case in dipole approximation, we have to solve the time-dependent Schrödinger equation. Now, this is, of course, an exceedingly difficult task, and numerically has been achieved maybe for H2 in a laser field, maybe not even that. So it's difficult. And the standard approach to deal with the full electron-nuclear problem involves 2 steps. The first step is we drop the nuclear kinetic energy in the previous Hamiltonian. Well, then we are left with this Hamiltonian where the nuclear coordinates enter only as parameters. So the first step is you solve the electronic problem, the correlated electronic problem for each fixed nuclear positions. Right? And as a consequence, then the eigenfunctions, they are known as Born-Oppenheimer eigenfunctions, and the eigenvalues are functions of the nuclear coordinates. So this is known as the electronic structure problem, which is a formidable problem in its own right, as we saw in the previous talk. So that's electronic structure problem, and these guys here, this is a cartoon, that's the so-called Born-Oppenheimer potential energy surfaces. So it's the eigenvalues of this Hamilton as a function of nuclear coordinates. It's a high-dimensional space in general, so this is just a cartoon. Now, second step that is almost always done is what is known as adiabatic approximation, where we approximate the full electron-nuclear wave function by a single product of this kind. So it's a nuclear wave function times one and only one of these Born-Oppenheimer states. Right? We take one of those, but at all nuclear positions, ideally. So this guy is fixed. And then that guy is the solution of a Schrödinger equation where the eigenfunctions, the eigenfunction of this guy as a function of nuclear coordinates acts as scalar potential. So that's the adiabatic approximation. Right? And you see immediately why this is useful, because it achieves a separation of the 2 types of degrees of freedom. Right? We have, on one hand, an equation for the electronic degrees of freedom at fixed nuclear positions, and then we have another equation for the nuclear degrees of freedom. Also, a point not to be underestimated is the fact that this electronic structure problem with fixed nuclei is really fixing our intuition of what a molecule is. Right? If we tried to do this with the previous Hamiltonian, with this one, and calculate, for example, the electronic density. Right? This is a constant. This Hamiltonian has translational symmetry. So if you think of a molecule, each point in space is equally likely. So the density, the electronic density that comes from an eigenfunction of this Hamiltonian is a constant. It's a constant for all atoms, molecules, and solids. So it's not useful, right? It's not our intuition of how we internally picture a molecule, right? If we think of a molecule as a scientist, we always think of a Born-Oppenheimer molecule. But it's an approximation, right? So one has to keep this in mind. Okay, so that's the adiabatic approximation. There is a second one, which is similar, but I want to mention it here. So it also rests on one fixed Born-Oppenheimer state at all nuclear positions, but the nuclear factor is a different one. Namely, you plug this into the stationary action principle and determine the variationally best, the stationary point, for this nuclear wave function, and then you get an equation of motion from the variational principle that looks like this. So on one hand, the scalar potential is a different one. It not only contains the Born-Oppenheimer potential surface that we had already before, but an additional term here. I come back to that in a second. And moreover, the kinetic energy is not just the Laplacian, but we also have a vector potential. And this vector potential has the form of a so-called Berry connection. So what this notation means, we write it from now on in this way. We have the nuclear momentum operator here that acts on the parameter dependence. So it acts on the subscript. And then we integrate out all the electronic degrees of freedom. So the bra and cat here mean integration over the electronic variables. So this is known as a Berry connection. And the line integral of this guy, if you integrate over singularity of the Born-Oppenheimer surface, that's the so-called Berry phase. So it's a popular topic. This Berry phase, and I will come back to that later in my talk, is tied, as you saw, to the adiabatic approximation. Right? That's fundamental. Berry phase always means adiabatic approximation. Okay, so that's the variationally best adiabatic approximation. One Born-Oppenheimer state, but a slightly different nuclear wave function. Okay, now where does this approximation come from? Is it a good approximation? What have we neglected in writing it down? And there is useful to compare with a formally exact representation of the full electron-nuclear wave function. And that's the so-called Born-Huang expansions written down here. So if you imagine you fix the nuclear position at a given point, then this is, and a given time, then this is just a function of electronic coordinates. So it's an element of the electronic Hilbert space. And these Born-Oppenheimer states are a complete set in the electronic Hilbert space, so we can expand this wave function at fixed capital R and T in the complete set of Born-Oppenheimer states. And then if we do this at each nuclear configuration, then clearly the coefficients of this expansion become dependent on the chosen nuclear position and on time. So that's a formally exact representation of the full wave function. And if one plugs this back into the time-dependent Schrödinger equation, multiplies from the left with the Born-Oppenheimer state, one gets this well-known set of equations for these coefficients. It's a coupled set of partial differential equations for these coefficients. And what appears here is the so-called non-adiabatic coupling matrix of first and second order. So this, with the definition that I mentioned before, it's a nuclear momentum operator. It acts on the subscript, and bracket means that we integrate out the electronic degrees of freedom. Now, if we neglect those guys, first order and second order non-adiabatic couplings, then we get back the nuclear Schrödinger equation that we had before. Right? So adiabatic approximation, the simple adiabatic approximation that I mentioned before, means neglecting all but one non-adiabatic couplings. It looks like a terrible approximation. I've thrown away almost everything, right? Now, turns out if one neglects only the off-diagonal non-adiabatic coupling matrix elements, then after a few lines of algebra, one ends up with the variationally best adiabatic approximation that I mentioned before. So you see that the diagonal term of these non-adiabatic couplings, that's exactly this Berry connection vector potential that we had before, and like any vector potential, it couples to the nuclear momentum. So this is really then plays the role of a vector potential in the Schrödinger equation, and this can be rearranged with these two terms, and you end up indeed with the variationally best adiabatic approximation. Okay. So it looks like a terrible approximation, but because you neglect almost everything, almost all terms, infinitely many terms of the Born-Huang expansion. However, if you look at these guys here, so this matrix elements, so as I said, you integrate out the electronic degrees of freedom, so those are functions of the nuclear coordinates. And if you look at those guys, right, then you find that they actually are mostly zero. So very, very small. Not exactly zero, but super small. Only when these Born-Oppenheimer potential energy surfaces come close to each other, either have a narrow avoided crossing or a conical intersection. In that case, in the vicinity of these regions in the nuclear space, those guys are large. But otherwise, they're very, very small. So then you see that if you think of vibrational spectroscopy, right, when you have phonons or molecular vibrations, right, then typically on a Born-Oppenheimer surface near the minimum, there's no conical intersection. So you have to go far away. Here's maybe a conical intersection, but it doesn't matter, right? At the place where you want to calculate your variational spectrum, these non-adiabatic couplings are actually negligible. So for vibrational spectroscopy, the adiabatic approximation is extremely good approximation. And in addition, and this must not be confused with a harmonic approximation, where in addition, this surface is approximated by a quadratic form. So that's an additional approximation that is often made, but it's not super necessary. Okay. Now, when does this approximation, the adiabatic approximation, fail? There's many cases where it fails, but I will show you two generic situations. One is the world of photochemistry, one could say. So typically, and that's the prototypical experiment, if you start with a vibrational wave packet that lives here happily in the minimum of the lowest Born-Oppenheimer potential energy surface, if you then excite the electrons. Electrons means I go from one electronic state to another electronic state. That's the electronic eigenvalues, remember? So I go up here, and I do this with a very short laser pulse, femtosecond laser pulse, let's say, so a time scale on which the nuclei don't move. So I excite very fast the electronic system, the nuclear wave packet stays as it was before, but then it realizes, now I'm in a scalar potential of which I'm not an eigenfunction, so it starts moving. So this guy starts moving, and then maybe at some point there's a conical intersection, so this nuclear wave packet splits into this part and another part, and maybe there's another possibility, so it splits again, and maybe ultimately it comes back to the ground state, and this is what is known as optical cycle. This is the basis of the process of vision in our eyes, and so that's photochemistry. And here you see immediately, you need more than one potential energy surface, at least two, right? Otherwise, so adiabatic approximation doesn't work. Adiabatic approximation means one potential energy surface, one and only one. And I should say many chemical reactions happen on the lowest surface, right? So you get something here and then you move around. Many chemical reactions are of that kind, but not photochemistry. So not the process of vision. There it fails. Now another very different failure of the adiabatic approximation. Imagine some kind of nuclear motion, vibration, or an isomerization, just something. And you ask the question, what do the electrons do? And of course the immediate answer is, roughly speaking, the electrons move with the nuclei because they quickly adjust to the nuclear motion. So then, if you try to calculate something like the time-dependent electronic density that is associated with this nuclear motion, and you use the adiabatic approximation, well, you just calculate the density with this approximation, so you take the absolute square of that wave function, integrate out the nuclear degrees of freedom, and then you get a time-dependent electronic density. N-body density or one-body density is not important for this argument here. And that's perfect. That's very accurate, close to experiment. But then you try the same thing with the electronic current density. So you evaluate the expectation value of the current density operator, electronic current density operator, so that involves an imaginary part, and here the derivative with respect to the electronic coordinates. Right? So you end up with this expression. Yeah. But Born-Oppenheimer states are most of the time real valued functions. Only when you have an intersection, so if you have a degeneracy at a particular nuclear configuration, then you may have imaginary parts, but always in between they are real. So the imaginary part is zero. Complete disaster, right? The adiabatic approximation tells you that the electronic current density is zero. But it isn't zero. Of course, the electrons move around with the nuclei, but that's a failure of the adiabatic approximation. Now, this turns out to be a particularly hard problem. So if you find this, well, what can you do? You can go back to the Born-Huang expansion and try to solve these equations as well as possible. But then, turns out, if you try that for this specific problem, many terms of the Born-Huang expansion, hundreds, are necessary. So eigenfunctions, these complicated electronic structure eigenfunctions in which you expand, you need hundreds of them. Super difficult problem. And I know some colleagues, Björn Manz, some of you may know him, the chemists among you, he spent decades on this problem. So it's super difficult. Okay, so as I said, when the adiabatic approximation fails, one can always go back to the Born-Huang expansion, but often this is really numerically not feasible. Like I said, when you need many terms, another case where you need many terms is when the Born-Oppenheimer states are dense. So that's in a solid, right? So densely arranged. So I have not seen any Born-Huang expansion for solids so far. I think it's not possible numerically. Then also if you have a strong initial excitation so that the initial state occupies many many Born-Oppenheimer states initially, then it's also, you need many states, and it's also difficult. Okay, so what can you do? One thing that one often likes to do is to treat the nuclear motion classically or semi-classically. But then you run into a problem immediately for this kind of case that I showed before. So, right, you excite a nuclear, an electronic state from this electronic surface to this one. Nuclear wave packet starts moving, it starts oscillating in this upper surface. But then whenever it goes across this avoided crossing, then the nuclear wave packet splits, and there's contributions that move on that surface going out. And this is a prototypical experiment. Ahmed Sevail got the Nobel Prize for it in 1999. So this is accepted knowledge. So this is what is happening. But then, when the nuclear wave packet splits, right, so one part oscillates on the blue surface, and the other one dissociates. So you have a probability for dissociation and a probability for vibration. What do you do with the classical trajectory? Right? What is that? Right? You kind of need one trajectory here, another trajectory here. And moreover, what is the force then on the nuclear degrees of freedom? Is it the gradient of the blue curve or the gradient of the red curve? So there's a problem, right? If you want to treat this kind of non-adiabatic problems. And this question, what the classical force is, I will demonstrate later that there's actually a unique answer to this. Okay, so the way we approach this problem is what became known as the exact factorization. So this is a way of writing the full electron-nuclear wave function as a single product. So it's like the adiabatic approximation. So there's a nuclear wave function, like in the adiabatic approximation, but here the electronic one is different. So it is, first of all, time-dependent, and it's not a Born-Oppenheimer state. So it's different. Okay, but in a nutshell, it means this. So you have the full electron-nuclear problem, and you decompose it into an equation for the electrons and an equation for the nuclei. Right? So for these two factors. So you achieve what you achieve with the adiabatic approximation as well. Right? You have a decoupling into two separate equations. Right? And that's the main advantage of it. Ultimately, you can do the traditional good old electronic structure approximations, anything that Peter showed you, or other approximations, density functional theory. You can apply this to this equation. And you can apply other things, like mathematics has this method of characteristics, where you approximate this guy by a swarm of trajectories. It's formally exact. Okay, so here's the first theorem. Tells you that the full wave function actually can be written in this way. And the important thing is that this electronic factor is normalized to 1 for each fixed nuclear configuration and each time. This means that this guy actually has the meaning of a conditional probability amplitude. Right? So the absolute square of this guy is the probability of finding the electrons at little r given the nuclei are at capital R.
Can I ask one question?
Yep.
Can you go back to the slide before?
Yep.
You're making a choice in the. You make a choice in the order which one you solve first, or how you extract one from the other.
Yes. Yes. It's deliberately asymmetric. In fact, we did both. Right? So you can make the electrons conditional to the nuclei, or you can make the nuclei conditional to the electrons. Both is possible. Both is exact on that level. But it's useful in different situations. So there is cases when electrons move more slowly than the nuclei. right? So if this is a nuclear vibration, and if you have a high Rydberg wave packet of the electrons, for example, this is one example, then the electrons move slower than the nuclei. So then this inverse factorization is useful.
So, just to understand, the HE there is not just the electron-only Hamiltonian.
No, I will, in a second you'll see what it exactly is. Yeah. Okay, so that's the first theorem. Now, knowing that the meaning of this is a conditional probability amplitude, then this whole factorization is actually a triviality. Right? Because think of the absolute square of the left-hand side. That's the joint probability of finding the electrons at little r and the nuclei at capital R at time t. And as you know, any joint probability can be written as a conditional probability times a marginal probability. And that's all there is here. Well, it's for the absolute square of that equation. So you need to make sure that if you multiply this guy with e to the minus I theta of capital R and this one e to the plus I capital R, which is the same factorization, that then this doesn't change anything. And indeed, this corresponds to a gauge transformation of the equations that I'm going to show you. So then it's perfectly fine. Okay, I quit this. So here are now the equations. Yeah?
So that factorization, is that an exact statement?
Yes.
Okay.
Yes.
I have trouble reconciling that with the Born-Huang, because if I would look at that as, let's say, if I would do a spectral decomposition of that, and I take like R and capital R as degrees of freedom, I expect a rank somewhere, a coupling between the...
Well, that's an important point.
This, right?
This is not a Born-Oppenheimer state. So this is important. So you could think of actually making a Born-Huang expansion for this guy as well. And then the two are trivially related. So there's no contradiction. If this was a Born-Oppenheimer state, then you couldn't do it. But this is general.
And the Born-Huang?
Born-Huang is a different way. It's also a formally exact way of writing that same object, the exact wave function. Both is correct, both is fine, and they live happily with each other.
Could you do then, let's say, spectral decomposition and get to your
Sure, it's a way of writing this object, and this object can be written as Born-Huang. So they are related, yes. Okay. So that's the first theorem. Then, actually, so I make this side remark. This idea of formulating quantum mechanics in terms of conditional amplitudes is actually an old one. Goes back to von Neumann. And it's very interesting to read this. It's in a local newspaper, appeared, Göttinger Nachrichten. Now this is very general, applies to any kind of conditional probability. Then later, 1975, Jeffrey Hunter really looked at electrons and nuclei, but strangely, none of these people actually then determined the equation of motion for the two factors, which is easy to do, right? You just plug it into the variational principle and then you get the two equations. And this is what you have here now. Okay, so let's look at the nuclear equation first. So that's a nice Schrödinger equation. You have a scalar potential, a vector potential. And there are n-body operators, so you have the full set of nuclear positions here, both the scalar potential and the vector potential. But otherwise, it's a nice Schrödinger equation. The electronic equation is more complicated. So first of all, here's the Born-Oppenheimer part. And then there's these two terms, And first of all, the vector potential appears in the electronic equation, which is kind of unusual. Also, the nuclear wave function appears here, grad chi over chi. So if you wanted to solve these equations numerically, you would have to propagate them in parallel. And then there's these terms. This is a nuclear momentum operator. So like in the non-adiabatic coupling terms, it acts on the subscript here. So strictly speaking, this is not an operator in the electronic Hilbert space, but rather it's a derivative with respect to a parametric dependence. So it's like the ID by dt in the Schrödinger equation, right? So it's not forbidden, but okay, this is what you get. So comparing with the adiabatic approximation, one difference here is that both the vector potential and the scalar potential are time-dependent. This was not the case. In the adiabatic approximation, there, this guy and this guy, they were static. Then you have in the electronic equation the Born-Oppenheimer part, but then you have additional terms here, and you have time dependence. Now, a very important part is that if you write this whole equation, let's say in a chosen unit system, let's say atomic units, then you find that these terms here, if capital M is now measuring the nuclear masses as multiples of a reference mass, let's say proton mass, then you get a dimensionless prefactor, which is the ratio of electronic over nuclear mass. So you have a theory with a small parameter. And that's wonderful. And that's a comfortable situation that in the electronic structure problem you hardly ever have. And so this is a small number. And if you look at this, well, this really screams for being treated in perturbation theory. Right? This is a really small number. So, and this is what we will do later, we will treat these two terms in lowest order perturbation theory. So, first order perturbation theory. Lowest order is the Born-Oppenheimer problem, electronic structure problem, and then next order, non-adiabatic terms are treated in lowest order perturbation theory. Okay, so here's this vector potential. Again, it has the structure of a Berry connection. And the time-dependent potential energy surface is an expectation value of the Born-Oppenheimer Hamiltonian, but importantly, not of a Born-Oppenheimer state, but of this time-dependent electronic wave function. So this is, roughly speaking, a linear combination of Born-Oppenheimer states. Then this term here, which is actually a Fubini-Studi metric, so we call it the geometric contribution. That's a separate story. I'm not going to talk about this. And this follows from gauge invariance. So nuclear equation is nice. You have n-body interactions, vector potential and scalar potential. But the electronic equation is somewhat unusual. First of all, it's a nonlinear equation in the electronic wave function because the vector potential appears, so this makes it nonlinear. Then there's these non-adiabatic terms, derivatives with respect to the parameter. Now, if you investigate these terms, the right-hand side of this equation, you realize that this is actually a non-Hermitian operator. So if you write this whole thing, let's say in the Born-Oppenheimer basis, you realize it's non-Hermitian. But it's the kind of hermiticity that still conserves the norm if you propagate it. So it's non-unitary, but it preserves the norm of the state, and but doesn't keep originally orthogonal vectors orthogonal. So a unitary propagation does two things. On one hand, it keeps the norm, and on the other hand, it keeps initially orthogonal vectors orthogonal when you propagate. And there's a type of non-unitarity, and that's exactly our case, where you keep the norm, right? So that you don't lose electrons, right? The electronic wave function is normalized, but you don't keep the orthogonality. And it turns out that it's exactly this property that is essential for the description of decoherence. This will be one topic, one application of that theory. And if you think about it, that's exactly what it should be. You don't want to lose electrons, and you don't, but something has to decay. It's the off-diagonal elements of the reduced electronic density matrix. I'll come back to that. So that's essential for decoherence. Now, an important point is, so on the exact level, well, this is fully equivalent to the full Schrödinger equation. One could get the idea that maybe by propagating these two equations, it's numerically easier, but it's not. It's harder. So, well, it's a nonlinear problem. It's non-Hermitian. It's all kinds of complications in the electronic equation that you usually don't want. So the idea is not to propagate really the exact equations instead of the full Schrödinger equation. But it's useful to, it's a useful starting point to make approximations, right? Because you can, having two separate equations, you can then invoke different approximations for the two types of particles. Okay. So let's first have a look at this problem that I mentioned before in the calculation of the electronic flux density that is associated with a slow nuclear motion. Right? So where this disaster happened, that the electronic flux is zero in adiabatic approximation. Okay, and there the idea will be that we treat these non-adiabatic terms in lowest order perturbation theory. So we use the fact that we have a small parameter here. Now we first tested that for a simple model system, just to fix the ideas. So that's the potential terms of the Hamiltonian. If you solve the corresponding Born-Oppenheimer problem, you see this is it's designed in this way, so you have this kind of double well. And if your initial, so that's the lowest 20 Born-Oppenheimer surfaces, and if you start your nuclear wave packet propagation here, then what you expect is that you have a tunneling oscillation. And so that's the nuclear wave packet, but the electrons move with the nuclei. That's exactly what you expect. And so then I'm showing you here a snapshot after a quarter of the oscillation period, where half, so to say, half of this wave packet is moved to the other side. So that's what you see here. That's the nuclear wave packet. As I said, part of it has moved to the other side. It's a snapshot. This is the nuclear current density. So it's 0 here, but it's still moving because only half of it has tunneled through. So this is the large value of the nuclear current density. And now the interesting part, the electronic current density. So it's a simple model Hamiltonian, so you can do everything exactly. You can solve the electronic problem, electronic density, and the electronic current density, so you get what you expect, namely that with this nuclear wave packet, the electrons also move to the other side. This is the quantity which in adiabatic approximation is 0, the disaster that happened. Now, if you do what I said, if you treat these non-adiabatic terms in lowest order perturbation theory, then you get this. And if you look at the numbers, they are really very close. So remember, this, if you try to do it with the Born-Huang expansion, it's a super difficult problem. And we tried that. We need 100 Born-Oppenheimer states in the Born-Huang expansion. So this shows you the advantage of the exact factorization, right? Who would have expected that treating this term in lowest order perturbation theory is equivalent to having 100 terms of the Born-Huang expansion, right? This is so this tells you it helps enormously. Okay, should I mention that? Maybe not. So this is just a demonstration where this electronic current density is important in the real world, and this is a particular phenomenon that's known as vibrational circular dichorism, where the interesting quantity is this so-called rotational strength, which involves magnetic dipole moment and the time derivative of electric dipole moment. And those are exactly this momentum and angular momentum currents that in adiabatic approximation are zero. So this has an electronic contribution and a nuclear contribution, and in adiabatic approximation, these guys are simply zero. And we treat this, I'm not going to say the details. This is a side remark. One can use this wonderful fact of having a small parameter also in other contexts, and we did this in our density functional approach to superconductivity. And and this is the message here, if you treat everything in lowest order perturbation theory in the terms that are proportional to this small parameter, if you do that consistently, which is hard to do, but you can do it, then you really have a predictive theory of phonon-driven superconductivity. So you can really predict critical temperatures. There are no fudge factors or anything. This is what we do here. This is the predicted critical temperatures. Okay, now, so far we talked about the electrons, so non-adiabatic effects in the electronic motion. But there's also non-adiabatic effects in nuclear motion. So, and here, compared to the adiabatic approximation, the difference is the time dependence here and here. So what's the importance of the time dependence? Well, this is an exact time-dependent potential energy surface. And how does it look like? So let's have a look at this. And again, just to fix ideas, we at first look at a nuclear wave packet. This is for a one-dimensional model of H2 with with simple forces, so we can solve everything numerically exactly. Those are the two Born-Oppenheimer surfaces. And we start the propagation with a nuclear wave packet that is up here. So that nuclear wave packet moves. And what is in red here is at each snapshot the exact, at that point in time, exact time-dependent potential energy surface. So initially, of course, it agrees with the upper Born-Oppenheimer surface. And then this wave packet goes across this non-adiabatic region. And then something funny starts developing here. Then happens what one expects, namely that the nuclear wave packet splits. That's exactly what I showed you before. And at the same time, this exact surface develops a step. And one can actually prove that when the overlap of these two split-off parts of the nuclear wave packet becomes exponentially small, that then this step here becomes infinitely steep. Now, what tells this? It's clear that, so the gradient, roughly speaking, of this exact surface, it would be the exact force. If the nuclei are here, in this region of nuclear space, well, it's the gradient of the upper surface. If the nuclei are here, it's the gradient of the lower surface. This is what it tells you. And this step is exactly what, you may have heard of that, these surface hopping algorithms do. So this is like surface hopping, except that it's exact. Right? So this is, in a way, a justification of surface hopping. This is what you get. So it's just a weird way of presenting the time-dependent Schrödinger equation.
That's very neat. The window, is that because of the way to the numerical application? Yeah.
Yes.
That you put it on
That's just numerics. So you see these spikes here. So I'm totally honest here. I just plot what comes out of the computer. So at this point, the nuclear wave, the nuclear density is 10 to the minus 40. So this is pure numerics. So that's numerical, as you say. This is window. That's purely numerical reasons. Okay, so that's the time dependence of the exact surface. So it's like surface hopping in a way. Now, what can we say about this vector potential? And here comes an interesting thing. So if you ask yourself, what is the total momentum of the nuclei? Well, it's the nuclear momentum operator to be evaluated with a full electron-nuclear wave function. Right? That's the true expectation value. So you integrate out the electronic degrees of freedom. And likewise here, right, you integrate out everything. If you do this, you can prove that instead of using the full wave function here, you can evaluate the nuclear the nuclear momentum and the nuclear angular momentum just from the electronic factor, from the nuclear factor. Now this is unusual. Let's take a step back. Right? Usually when we have a two-component system, we have to calculate expectation values from a reduced density matrix. Right? Not here. This is a pure state. But there is a reminiscence of this tracing out, namely that the vector potential here appears. Right? So you evaluate the momentum of a subsystem from the exact factor that describes that subsystem. But the momentum operator has to be enhanced by that Berry-type vector potential. And that's a rigorous statement. Right? You can easily prove it.
This is some cancellation, right? I mean, that these two are equal, you have to cancellate some integrals.
Yeah.
Cancellation problem.
Yes. So this does not apply to any observable, right? But for the momentum, it does. Right? So you're absolutely right. Yeah. Okay, so it also applies to the individual momenta, and then we can deduce Ehrenfest equations, like we always do. Right? So we use the equations of motion and calculate the rate of change of the momentum of nucleus number mu, and likewise the rate of change of the angular momentum of nucleus mu. And we get these two, what we call subsystem Ehrenfest equations. What appears there is a force operator. And this force operator consists of two parts. A red part, the red part is electromagnetic, like. So there's something like an electric field, which is A dot minus gradient of the scalar potential. So that's like in electromagnetism, except that it's not electromagnetic. Right? Because this vector potential is a Berry connection, right? And there's also a Lorentz-like force, so it's the curl of this vector potential which acts as magnetic field and as velocity operator. So this is electromagnetic-like. But remember, this guy here, the vector potential, also the scalar potential, that's a function of all nuclear coordinates. Right? And this is an important difference to electromagnetism. In electromagnetism, the vector potential is only a function of one coordinate vector. And this leads to the fact that there's these blue terms which do not have any classical analog. And this can be viewed, here's the formula, as a Lorentz-like force where the magnetic field involves a curl of the vector potential, but the derivative here, let's say that's the vector potential A1 that acts on the nucleus number 1, but the derivative here is the derivative with respect to nucleus number 2. Right? Since A depends on all the nuclear coordinates, you get terms of this kind. No classical analog of this. We call it an internuclear Berry curvature. So this is what you get. So this is subsystem Ehrenfest dynamics. They also can be evaluated in the classical limit. In fact, we did this first many years ago. And then in an algorithm that I might have time to show you, they also appear. Now, what I want to emphasize here, those are the true forces on the nuclei. So if you ever wondered, if you have an electron-nuclear system, what are the forces on the nuclei? This is it. There's no choices, right? This is the forces. Okay, now one thing that I also want to mention or emphasize is this whole factorization business. You can do it for anything. Right? You can do it actually, and we did that for the electronic structure problem as well. Right? You have an n-electron wave function. It's a joint probability, so you can again rewrite it as a marginal probability times a conditional probability. For example, you can factor out 2 electrons, right? And then it's conditional to the others, right? So that's one choice. And we treat it in this way. It's useful when you have different kinds of electrons. For example, slow electrons and fast electrons. So fast electrons are the ones in the core. Slow electrons are the ones that ionize and maybe come back and produce harmonics. So this is one thing that we did. Another thing that we did was strongly correlated and weakly correlated electrons in a solid. Right? So again, 2 types of electrons. You can do that. And in all cases that you may think of, you have these exact forces. Right? For me, it's mysterious enough to even in adiabatic approximation, when you start with a Coulomb Hamiltonian, that the force approximately is a harmonic oscillator for the nuclei. If you look at the Coulomb Hamiltonian, this is not at all obvious. I find it not obvious. And okay, this comes out. And this is the exactification of that, so to say. Now, are these Lorentz forces important? There's one interesting case. If you have, where they are large, if you have an atom that enters a magnetic field, you can ask yourself, what is the trajectory of that atom? So if it's a neutral atom, the intuitive answer would be it's a straight line. But then, these Lorentz forces, they act on the electrons, they act on the nucleus. It's actually kind of complicated if you take it seriously. And it turns out that for this particular case, a single neutral atom moving in a magnetic field, this Berry connection force exactly cancels the external magnetic field. So indeed, it's a straight line. So this is one case where it's important. And other cases, it's important in an electronic water wheel that we investigated. Don't have time to discuss that. So how are we doing on time? I'm probably basically out. I want to show you one more thing, which is decoherence. Right? So some of you are interested in quantum computing. And what is the standard currently, if I understand correctly, is to kind of accept decoherence as a God-given fact, and you then have these error-tolerant algorithms, which is, in a way, I understand it, a workaround. But then maybe it's better to try to understand decoherence and maybe ultimately find ways to control it. Right? So decoherence is what? So if you take, and it's again for this case of electrons and nuclei, but you can do it for electronic and nuclear spins, you can do it for anything. So we first of all look at the electronic reduced density matrix of the electronic subsystem. So we trace out the nuclear coordinates, as written here. And then one speaks of decoherence when the off-diagonal elements for large time go to zero. Off-diagonal elements of this guy. So this is a basis-dependent measure of decoherence. And there's a better one, which we also saw during the previous talks, which is the purity, which is the trace of the square of this object. So ultimately, if you look at these things, very similar in the end. Now, so what does that mean? If the off-diagonal elements go to zero, it means that it's essentially a transition from a pure state density matrix to a classical ensemble. So you, in that sense, you lose the quantumness of your system, right? And well, if you want to do quantum computing, and after this so-called coherence time, in which these terms go to zero, your quantum system is not the quantum system anymore, but the classical system, then you have a problem. So when I say here we want to control decoherence, it means that we want to make the time scale on which the system decoheres as long as possible. Right? If we can find conditions such that the decoherence time is comparable to the age of the universe, then no problem. Then we can do quantum computing. If it's a few femtoseconds, then we have a problem. Right? Then we cannot do quantum computing anymore. So that's the idea of this project. And now we use, in this reduced density matrix of the electronic subsystem, the exact factorization. We just plug it in here. And then we get something interesting, namely, it's an alternative, somewhat unusual way of writing the reduced density matrix, namely in terms of a pure state density matrix that depends on a parameter, which are the nuclear coordinates. So we call it the conditional reduced density matrix. And then you multiply this with the nuclear density, right? So the absolute square of the nuclear factor. And then we get the reduced density matrix. So now we do an approximation, namely classical approximation for the nuclei. So we replace this nuclear density by a delta function involving a single trajectory. So this is clearly an approximation, right? First time here that I do an approximation. Then the reduced density matrix actually reduces to a pure state RDM, right? Namely along the classical trajectory. So then, if you ask people in the molecular dynamics community, can we still describe decoherence with this pure state RDM? And probably 100% of the people you ask would say, no, it's not possible. You have lost decoherence here. And indeed, if you think of algorithms like Ehrenfest dynamics, you can't do it, right? Ehrenfest dynamics is well known for the fact that you cannot describe decoherence with a single trajectory. Now, the difference to Ehrenfest dynamics is that the electronic state in Ehrenfest dynamics is it's a mean field state. It satisfies a unitary time propagation, while this is the electronic factor. And I emphasized before that this satisfies a non-unitary propagation. Right? And it is this fact that ultimately, for this prototypical case, where you have a splitting of the nuclear wave packet with the two coefficients chi0 and chi1, one can easily prove, this is a well-known result, that the off-diagonal element of the reduced density matrix is this superposition. And it turns out that with this non-unitary propagation, one can actually get a very good account of this number as a function of time, but using a non-unitary propagation of that object. So that's the message. We can do it, and okay, that's all I want to say.